All right, great. So I mentioned BitZip in my last talk. This talk is about that. It's based on ideas that were originally published by Ethan Heilman. And it's basically about how do we deal with the size of post-quantum signatures if we were to implement post-quantum signatures in L1. So the main problem is that these post-quantum signatures are big, like really big. We use this single small block to represent the size of a SEC P256K1 signature, specifically with ECDSA. And we can see that these post-quantum signatures are in some cases like 30, 40 times bigger or more. And so if we do nothing with the Bitcoin block size limit, then that is going to inherently constrain throughput on Bitcoin layer 1 and reduce our transaction throughput, scalability. So BitZip is attempting to address this, basically preserve or potentially even improve throughput without having to increase the Bitcoin block size limit. So what if we just got rid of the signatures? It's kind of crazy sounding idea when you first encounter it. And so the next question, of course, is how? How do you do that? And so that's where BitZip comes into play. So what is BitZip? It one adds a new. You of course assumes a new post-quantum transaction type in Bitcoin layer 1. And then it adds a new block validity rule that says there cannot be any post-quantum keys or signatures in the block. Instead, we provide a single Stark proof that proves the validity of all of the post-quantum transactions that are included in the block. So this is not an anatomically correct representation of a Bitcoin block, but at a high level, you have a bunch of transactions. Those transactions essentially have two primary components, like the non-witness data and then the witness data. A little bit of a glitch. And then BitZip kind of changes this up, so we still keep the quantum vulnerable transaction types if we want to. It's implementation detail. But we add this second part of the block which actually contains all of the post-quantum transactions. And we have the non-witness data kind of represented by the smaller blocks, and then we have this single BitZip witness, which is a proof that all of these transactions are valid. So the users are going to broadcast their post-quantum transactions with the post-quantum signatures to the miners, and then the miners are going to prove that all of these transactions are valid as of the block that they're building. And then when they actually publish the block, they take out all of the witnesses from those transactions, those giant signatures, and replace it with this single cryptographic validity proof. And that's how you're able to get those transactions to be so much smaller, because you're not actually including the witnesses. And so to compare the kind of throughput that you get from that, again, we're kind of going to represent the current transactions per second as this single block. If you implement post-quantum signatures without BitZip, then in your best case scenario with one of the smaller signatures, you go from 11 transactions per second down to 1.69 transactions per second. And then with this BitZip technique, assuming that all of the transactions in the block have been BitZipped, you actually increase your transaction throughput from 11 transactions per second to 87 transactions per second. because we're stripping out all witness data and replacing it with this single cryptographic proof that gets amortized over all of the post-quantum transactions. So, again, a kind of visual representation of a Bitcoin transaction. We're either omitting, in the case of everything that is like shaded orange here, we're just stripping all of that out, and then for the stuff that's shaded black, we're able to like compress that significantly, and then just cryptographically prove using this validity proof that all of this stuff existed at some point and was valid at the time that the block was constructed. So here's that comparison chart again. Just to quickly summarize for folks who are watching this presentation independently, we've got these large post-quantum signature algorithms that produce signatures, SLH-DSA, about 8,000 bytes, MLDSA, almost 4,000 bytes, and these produce transactions per second on layer 1 of 0.82 and 1.69 transactions per second, respectively, whereas BitZip and some of the other post-quantum like proof-based aggregation systems like rollups or shielded CSV could actually increase our transactions per second and give us somewhere between 83 and 104 transactions per second. And this future proof column is referring to the fact that if improvements to the signature post-quantum signature system, or if a bug was found and we need to fix the bug, this would require a consensus change. So we consider that to be not future proof because we have to now go through a consensus change again, whereas with these other techniques like rollups or shielded CSV, at least at the transaction layer, we have some level of future proof because we can change the post-quantum cryptographic scheme that is being used without having to do any consensus changes. So it is future proof to a degree that the other post-quantum techniques are not. But yeah, so some open questions with the BitZip proposal are like, okay, we've reduced the amount of data that we have to put on chain. That's great, but we're still broadcasting these very large signatures over the wire, over the peer-to-peer network, into miners' mempools. Is there anything that we can do to reduce Bitcoin peer-to-peer bandwidth increases due to the larger size of these post-quantum signatures, pre-Starkification? That's a technical term that I just made up. Some ideas are that like users could interactively aggregate their signatures together ahead of time, or if like one user is like a power user that's receiving a lot of transactions and sending a lot of transactions, then they might be able to aggregate a lot of these things together and maybe do some cut-throughs and things like that before sending that on to the miner with their own validity proof that the miner can then kind of recursively include in the final proof that actually goes on chain. But yeah, it's kind of an open question. There are some ideas, but there could be more potential solutions there. There's a question about like, how does fee bumping work for these post-quantum transactions? So, once a miner receives the transaction and it starts, producing this validity proof, and then they receive an RBF or, that proof that they've been working on is no longer valid. So they either have to throw that proof away, replace the transaction and start over, or ignore that RBF. It's not as easy to do an RBF as it is in kind of the mining world today. So that's an open question. How can we prevent in mempool and in block starkification from becoming a centralizing force that harms censorship resistance? So, if there are these incentives for users to, say, aggregate their transactions beforehand, maybe does that create a centralization that could affect censorship resistance, especially if the users who are doing that are maybe paying a lower fee than the users that are not. And so it just becomes more expensive for users to deal directly with the miners. Or, even at the mining layer itself, if all the miners are using like one big beefy machine to do this proving, like kind of sharing it like old school mainframe style, that's a point of centralization, and is something to be considered. So, yeah, open question there. And then important question to answer, especially for folks who've been paying attention to what's happening in like the ZK and validity proof space, is like, how can we mitigate against Stark verifier bugs? So this would be a verifier that's built into Bitcoin Core or another Bitcoin full node implementation. And if there's a bug in that verifier, then the node could be tricked into accepting a block that actually contains invalid transactions, which would be bad. And so, I was talking to one guy last night, and he said about this proposal, it was the first time he had encountered the proposal, but he said, I like non-negotiably, if it was up to him, he would require there to be like multiple verifiers or multiple verifier implementations. Just because if there was only a single implementation and it had a bug, then it could lead to a permanent kind of loss of funds. Whereas if you had multiple independent implementations, it's unlikely that they all have the same bug. And so you might actually be able to prevent that bug from causing like a catastrophic permanent loss of funds on the network. So yeah, I think actually like how do we roll this out in a way that's safe is also an open question. So again, I mentioned this is based on work by Ethan Heilman. This is a QR code for the post that he published on his blog about this. I think the post itself was kind of inspired by a lot of other similar kinds of work, including like work on rollups. But yeah, credit to Ethan for putting it together, and happy to take questions about it.
All right, we got one question.
Thank you for creating a great intuition for BitZip. I was wondering, like, do you have any numbers on like how long would like a get block template take to like do this aggregation? Like what on like a 3 gigahertz CPU? What are we talking?
No, I don't. Sorry.
Milliseconds, seconds, hours.
So there is a project called ZeroSync that is attempting to basically like Starkify the whole Bitcoin blockchain right now as a way of enabling people to quickly sync the blockchain. And I think proving the validity of a single block was estimated to be on the order of like tens of minutes, maybe hours. I don't remember what the kind of state of the art was at the last juncture of that project, but it wasn't like they weren't able to do it within the span of like a block. So it couldn't. I don't think it's practical for real time, quote unquote, real time proving at this point. But it was also, I think, fairly unoptimized at the time. So there's a lot of headroom for optimization, I think, still in proving Bitcoin consensus specifically.
Thanks for the great presentation. I had a somewhat related question on if you've looked into like if the miners would need like new hardware to be deployed or co-located, And slightly related is the if any of these signatures like over the network like compress well, or if you have looked into those.
In terms of hardware, you probably would want some kind of dedicated proving hardware, GPUs, or there are even people talking about like ZK ASICs, which, are just like hardware that's extremely optimized specifically for this kind of proving. And so you would probably want something like that to be competitive. And in terms of what was your other question?
I should have been more clear. The P2P message passing. If
Aggregating.
Aggregating.
Yeah,
if that compresses.
Yeah. I mean, I think it depends on the post-quantum signature algorithm that you're using. Maybe if the algorithm itself like lends itself to aggregation, either like interactive or otherwise, you could do something like that. I mean, one of the problems with like trying to non-interactively aggregate things in a peer-to-peer way with like random people is this kind of free rider problem when it comes to fees. I think Ethan could probably explain it better, but I think there's like a problem where if somebody else's transaction, I don't know, is like smaller than yours, and you aggregate your signatures like ahead of time, you might end up subsidizing some of their transactions or something like that. I forget the exact details, but I do have it in my mind that there is some kind of incentive or for like free rider problem with aggregating, trying to do this like signature or like non-interactive aggregation with random strangers.
Yeah, makes sense. Thanks.
Hey, great presentation. Have you modeled out or thought about kind of what the failure mode or what the behavior is if there's a reorg? Like if miners are going to generate a validity proof for the block and discard all the signatures, and then there's a reorg and not all of the transactions make it in, what happens now is unconfirmed transactions go back into the mempool, but if everybody's already dumped all of those signatures, then you might have transactions that miners can't generate proofs of without people rebroadcasting. So just as I was watching your talk, I was wondering, like, can you imagine an implementation where miners like hold on to signatures for a couple of blocks or something, or do something else to make sure that they still have witness data to regenerate proofs?
Yeah, that's exactly right. I think you would have to kind of switch to a model from immediately kind of flushing your mempool to like hanging on to those transactions for a while until you think that they're not going to be reordered.
6 blocks deep or something, or whatever it is.
And it could be a configurable parameter, but yeah.
Okay, well, give it up.
All right, yeah, thank you all.